Do you want a car that's not very expensive, but potentially can drive very far on a single charge? Or something maybe more on the sports car end of things that's beautiful, costs a lot, but maybe doesn't actually even drive that far. So we're getting to the point where there are so many options, particularly in transportation, that you can really customize it to the user and their personality. Now, this explosion, and explosion is probably not a good word, but the rapid movement toward electrifying transportation is really highlighting some challenges in supply chain, particularly where mineral resources are obtained. And in particular, I want you to think about roughly the size of a battery you need to put into a car, and how much lithium that would take. And so I'll come back to that at the end of my talk in terms of potential other solutions. I'll be very brief about how a battery works. For this webinar, if you're attending today, you probably already know this. I just want to highlight again the three main components: anode, cathode, and then some electrolyte that separates those two components. And really what we want to focus on today, I think in all three talks, is new chemistry for each of these components, as well as new ways of assembling these materials so that we can get even more functionality. So conventional lithium-ion batteries are what I call 2D batteries. These are all layers that are stacked or rolled. These are just 4 configurations from the famous Tarascon and Armand Nature review in 2001. You can get a cylindrical cell of various sizes. This is showing you one that's roughly a AA size cell, all the way to the example on the bottom right, which is what you would have in your cell phone. In all cases, there are current collectors, anode and cathode, and then some kind of a separator that either is soaked in a liquid as an electrolyte, or that's a polymer as the electrolyte. Certainly there are a lot of companies trying to innovate solid state batteries where the electrolyte would be, say, solid state ceramic. But in all cases, these layers get stacked or rolled. The problem with all batteries, all energy storage devices that I know of, are what happens at the interfaces, and the interfaces in these cells really are critical. So if I zoom into any one of those architectures I just showed you, the picture becomes more complex. In this case, I'm showing you a copper current collector on the top, some anode that is, say, graphite or graphite mixed with silicon with binders, conductive additives. There's some distribution of morphology and particle sizes. And so at every one of those interfaces, reactions can occur. Then we have our porous separator, say, liquid soaking the whole battery, and then on the bottom, a cathode material, which again is typically particulates that are combined with binders, conductive additives, and again, pretty high surface area. So for batteries, there's the thermodynamic aspect of the energy levels of the anode and cathode and how you combine those to get the overall voltage of the cell. But the interesting challenge really is in all of the kinetics and the side reactions that occur at all these interfaces. And for the 3D battery that I will show you today, the interfaces are very high, interfacial surface areas are very high, and so any unwanted reaction that happens at an interface will become exaggerated. And so we need to be very careful of that as we move toward 3D batteries. So why would you want a better architecture or a new architecture for a battery? I mentioned previously, I think of these as 2D batteries. And the challenge really is if you want high capacity, typically what people do is make the anode and cathode layers quite thick. And that results in very long diffusion paths, which you observe by having a battery that is very slow to charge and discharge. High power batteries are typically made by making very thin anode and cathode laminates and then stacking many of them. The challenge there then is the trade-off is low capacity, but you get very fast charging. And so people like Bruce, Deborah Rawlinson, Jeffrey Long innovated this whole theory or this idea of a 3D battery and really sketched out all the possible routes toward making a 3D battery, with the goal being completely interdigitating the anode and the cathode so that locally diffusion paths will be short. And that should result in being able to utilize the Z height of the battery much more effectively, which results in high capacity and fast charging. With appropriate choice of the chemistry that you use, then you can also make this battery pretty safe. So these are the kinds of problems that I love, where somebody's already predicted what the best solution should be, but then somebody needs to figure out how to make it. And by training, I really am a synthetic chemist. So the way that we thought about making this battery was shown in the graphic here, where we're going to start with copper foam. We chose electroplating because basically we made a list of all the equipment we could not use. And what I mean by that is I was thinking about things that were really expensive, really slow, where quality control would be very difficult to manage. Thinking about all of that, I arrived at electroplating, which is very widely known, also scaled to massive volumes in industries like the semiconductor industry, coating of, everything from mechanical parts, cars, Boeing 787s. So I knew that it could be used to coat structures with very high fidelity, but also it's a really good tool for making materials. And so the way that we start is with copper foam as our current collector. Copper is the common current collector in a lithium-ion battery for the anode anyway. And in this case, the surface area to volume ratio sets the ultimate top limit for the power density of the battery. We're going to use that copper foam as the working electrode to deposit our anodes. These are directly deposited intermetallics. They were chosen because they have very high capacities for lithium, but more importantly, they're really good metals. So that means we don't need to add any binders or additives. They can be used as the working electrode for the next piece, but also they dissipate heat very well, which is important at high power conditions. I'll tell you more about copper antimonide, which is the anode, the main anode I'll talk about today. But if that's the working electrode, we can then use it for step 3 to electrochemically polymerize or electrochemically coat a polymer electrolyte. We chose polymers because they are mechanically flexible and they can be designed to have very high breakdown voltages, which leads to safety in the battery. We then spray coat or print cathode slurries directly onto that polymer. So the polymer is our electrolyte and it is also our separator. And then the cathodes, we just use standard industry available cathode materials with binders and additives that can be dried, and then aluminum mesh is the current collector on that side. My dream was to make this as safe a process as possible. And so we've developed the processes here to be all water-based. So aqueous solutions that are stable for months at a time that can be scaled. And now we're trying to commercialize this technology in partnership with Stanley Black & Decker for power tools and Hercules electric vehicles. These 3D batteries then can be made by basically making a single piece, and I'll show you pictures of that. And then we can stack those pieces to increase capacity. So just like any other battery technology where you would want to stack layers, we can do the same thing. It's just in our case, a single layer is the full cell. And then we can hook these up in series or in parallel, depending on the voltage needed. Okay, so why copper antimonide, which is maybe an unusual choice? What we were looking for were anodes, again, that were really good metals. So we were looking for high capacity, but that in and of itself is not sufficient. It really has to be something that is metallic so that it can conduct electricity well without the need for binders. So here I'm showing you graphite, which is really the canonical anode material. 1 lithium atom per every 6 carbon atoms. And I'm showing you the capacities in gravimetric and volumetric terms. I'm showing you the pros, which in this case is good conductivity and a pretty small volume change upon lithiation. If you move to something like antimony, this is very similar to silicon in that it is a conversion alloy material. You're breaking bonds and making a new compound. So in this case, you're making lithium antimonide. The gravimetric and volumetric capacities are significantly higher, but lithium antimonide by itself is a pretty bad semiconductor, so the electronic conductivity is fairly low, and the volume change is pretty significant. The problem there, again, because we're not using binders, is we electrodeposit a dense film. And if you cycle that many times, because of the volume expansion, the anode will crack and you observe pulverization. That results in a pretty significant drop in retained capacity as a function of cycle number. If we move, however, to something like copper antimonide, we still make the same daughter compound, Li3Sb, but now you extrude 2 moles of copper, which act as a conductive matrix. There is a trade-off in terms of the gravimetric and the volumetric capacity, but the volumetric capacity is still significantly higher than what you would get with graphite. The films are much better in terms of conductivity, and the volume change is a little bit more modest. So we decided to focus on that as our first anode. And the first step was to figure out a way to electrodeposit this material directly out of solution. And remember that I told you we wanted aqueous solutions with, if possible, very safe chemistry. And so my very first graduate student, James Mosby, figured out how to do this using citric acid as a coordinating ligand. I'm showing you a cyclic voltammogram here in black at pH 1, which is the normal conditions for dissolving antimony salts, very low pH. The advantage of using citric acid is as you raise the pH, you can keep the antimony in solution. The electrochemical window shifts to much more negative potentials. And if you look at the two red peaks on the top right corner of the CV, if you hold your potential there, you can directly electrodeposit crystalline copper antimonide. So this is an X-ray diffraction pattern of a film that was deposited in 2 minutes. And again, it's just anomalous. It's so beautifully crystalline, deposited out of solution at room temperature. So in general, in my group, when we're trying to use anodes and trying to study how they behave, we follow this workflow. We use normal electrochemical cells. We plate onto large flags. This is the image I'm showing you on the top. That can be characterized with X-ray diffraction, scanning electron microscopy, energy dispersive spectroscopy, and we can look at these before and after cycling. We punch discs out and assemble them into swage lock cells that we can take apart. So we can do sort of post-mortem analysis of how these materials fail. And then we typically use differential capacity analysis so that we can look at how the peaks that correspond to distinct chemical reactions evolve over cycle number, over rate performance, changes in electrolyte composition. And this is a really sensitive way of observing changes as a function of various variables. So let me just show you quickly a few pictures. This is a low magnification SEM image of one of the foams that's been coated with copper antimonide. You do see that there are thickness differences where there are areas of high curvature, and we worked really hard actually to smooth those out. You see cubic faceting when you zoom in, and that's indicative of the structure of copper antimonide. When we fully assemble the cell, this is a low magnification cross-section image. You see the aluminum mesh current collector on the bottom. And really what you're looking at is the spray-coated cathode over the whole battery. We can freeze these in liquid nitrogen and cleave them. And here you're looking at a cross-section which really highlights some of the benefits of this architecture, but also some of the drawbacks. If you focus just on the image on the left, the first thing you notice is the copper foam is actually hollow. So the struts of the copper, because of how it's made, actually have some empty space. And we will need to be able to get rid of that in order to improve the overall energy density of the cell. You see the very thin layer of copper antimonide, the polymer electrolyte around it, and the cathode. And again, one of the advantages of electroplating is you can control how much material you plate for the anode side, and that's really important for capacity matching to the cathodes that we use. So some optical images now showing you some of the optimized cells that the company makes. This is an image on the left showing you our ultrasonically welded tab. That's where we're going to make contact for the electroplating, but then at the end, when the battery is packaged, that is the tab for the anode. And the image on the right shows you the copper antimonide really coating the foam pretty uniformly. It coats throughout the thickness of the foam. And in the company, we have spent quite a bit of time developing really good tools to be able to manage very high quality, high fidelity electroplating in very short amounts of time. This is what the cell looks like when it's coated with the polymer. It looks a little bit like clear nail polish, conformal coating. In this case, it is dry, and then we can spray coat the cathode. And here you see some texturing from the cathode drying. We do have to compress this at the end to try to densify the cathode. But what's really amazing is I'm going to show you some data in a moment comparing the 3D architecture to the 2D architecture. And it's really important to be able to compare apples to apples. So what we want to be able to do is compare this battery, this 3D battery, to a 2D battery made on copper foil, but made with the exact same process, the exact same materials, and importantly, the exact same capacities. And so what I'm showing you in the picture on the bottom right is a 2D battery on copper foil, but the exact same materials, copper antimonide, electroplated polymer, spray-coated cathode, and then the 3D battery on the top. And what you're seeing is the dramatic difference in footprint. Both of these have the exact same capacity, but the 3D battery is really utilizing its Z height a lot more effectively. So the overall footprint for the same capacity is much lower. So this actually works, how people predicted 3D batteries should work. What I'm showing you here is capacity in percentage. This is after the formation cycles. That's what we set as our 100% capacity, and then cycle number as a function of different rates going up to 20C, so full charge or discharge in 3 minutes. The green data is for the 3D interdigitated cells, and the red data is for the 2D cell. I do want to be very clear, though, for these batteries, we did gel the polymer with a liquid additive, and that's to enable low temperature performance. But what you can see from this is that the green battery really, the 3D battery does a much better job of retaining capacity at very high rates. Both architectures recover well, so the chemistry is pretty robust, but what you're seeing here is the effect of the architecture. So just to wrap up, that's a new way of putting together materials. I just want to spend 1 minute telling you the direction the group is going in now. We're focused now on looking at other antimonides and also other intermetallics that can balance different kinds of reactivities. All the elements I'm circling in red here follow the general reaction shown above, but they do have very different chemistries. Zinc antimonide, for example, both zinc and antimony lithiate. And so we're looking at the effects of electronic structure, mechanical stability, and chemistry in contact with electrolytes to determine whether or not we can expand this to other areas. We are moving toward sodium batteries. So in these plots, I'm just showing you, the cathodes typically used for lithium, the anodes used for lithium. And if you look at the analogous plot for sodium, you see that there are some examples where silicon, for example, doesn't sodiate. So we really need to look at new materials. And this is really thinking about applications where weight is not important. So if we're thinking about the scarcity of lithium, sodium is much more abundant, it's a lot cheaper, but it is heavier. And so we're thinking about ways to make better sodium batteries so that we can move toward applications like grid level storage. The very last slide, we can use differential capacity plots to study, in this case, antimony sodiating and desodiating. We see a lot of change over cycle number. We can assign each of these peaks to a distinct reaction, and we're seeing some pretty interesting chemistry that's happening from pressure in the films and the ability to sort of access kinetically stable phases that can help us store a lot of sodium. So with that, I just want to thank my group and the funding agencies. It's very cold in Colorado now, so this was a recent group picture. But with that, I'll turn it over to Jörg. I'll be happy to answer any questions when we get to the panel discussion part.
Awesome. Thank you so much, Amy. I'm going to ask I call it a quick question, though the answer may be very complex. And so maybe, just in a couple sentences, in the current battery version you have, the 3D battery, can you pinpoint what the rate limiting kind of component or aspect is in that battery right now?
That is a great question. The rate limiting component right now is actually the cathode slurry. And it's because we can't package under pressure the way a normal 2D battery can. So we will need to find clever ways of densifying the cathode. Yeah.
Awesome. Thank you so much. And we're going to get to that densification in the panel discussion. I got a couple of questions there as well. Well, thank you so much, Amy. Next up, we will have Professor Bruce Dunn, who may appear. There he is. So Professor Dunn is the Nippon-Shi Glass Professor of Material Science and Engineering at UCLA, and he's also the chair of the department there. Professor Dunn actually got his PhD at UCLA as well. And between the two stints at UCLA, he was a staff scientist at General Electric Research and Development Center. The research in the Dunn group focuses on the synthesis of inorganic and inorganic-organic hybrid materials, often using sol gel processes. And recently really was a focus both on 3D batteries as well as pseudocapacitive materials. Professor Dunn has received numerous honors, including the Orton Lectureship from the American Ceramic Society, a few DOE awards, and he is a fellow of the Materials Research Society as well as the American Ceramic Society. With that, I'll hand it over to Bruce. Please take it away.
Okay, thanks very much. I'm assuming you can see my screen okay? Okay, and you can hear me. Okay, then I'm all set. So first, let me thank Jorg and Emily for the invitation to come and participate in the workshop. It's been a great workshop. I haven't been able to go to all of them, but certainly it's been great fun. And in some respects, it's been so much fun. You really, really miss the in-person interactions because they would be awesome. Okay, I know that this talk is, or the seminar series to a large degree centers on electrification and grid storage, but my 3D batteries don't go in that direction. The 3D batteries that we do really are geared towards small devices. And this goes back almost 20 years. And it really has to do with when one of my colleagues, Chris Piester, was working on what's called smart dust, where you were able to do all sorts of sensing and communication in a small little chip, came to me and said, I need a battery and we're going to revolutionize the world. And he said, I don't need much. I just need about a joule per day. And I said, okay, how much, what do I have in terms of volume? He said, it's a cubic millimeter. That's no problem. I looked at thin film batteries and I knew very well from John Bates' work that you could definitely make beautiful thin film batteries where the energy density was on the order of 2 joules per cubic millimeter. The problem is the area. In the case of the smart dust, you only have a square millimeter. And so it means you need to have an energy density of a joule per square millimeter. In the case of the battery that John was making, it was 10 to the minus 2 joules per square millimeter. It wasn't close. You missed the mark by a factor of 100. And that really had an impact on us. It also said something else that we know very well. People know in Boston, we know throughout, certainly in California, real estate's expensive and it's valuable. And so when it comes to electronics, it's even more valuable. I'm going to see if I can put a pointer on over here. Excuse me for a second. And okay, good. Okay, so now you have the motivation of what we're going to try to do. Amy showed this. She did a terrific job of explaining why you go to 3D, and she explained what the issues were with 2D. This is another way of looking at this. Think of this in terms of multi-dimensional architectures. So in case if you need a large energy density, you make the cathode thicker. That's nice, but it decreases the power density. If you want something that goes to high power, go to thin films. That's great. So what do? You go in between. And that's the general idea behind the 3D battery concepts. And so the idea then is you're going to have, in our case here, and I'll show you some other designs as well. In our case, what we're doing is we are arranging an array of electrodes. And within any one of those individual electrodes, we're going to have a relatively short diffusion path. And that's the basic idea behind it. The other part of this is that if you want to increase the energy density, then what you do is you increase the length. You keep the distance between the electrodes the same. So that way the resistance, the impedance of the battery is not affected as you increase the energy density. In this respect, you are able to separate energy density from power density. And that is an enormous advantage when it comes to design. And design is what we did very early on. Perhaps the most, we already saw the sponge battery, which Amy explained very well, and of course works very nicely. But there are others that are based on more periodic arrangements. And I will be showing you a lot of work related to interdigitated geometries where you interdigitate anodes and cathodes. We'll spend a little bit of time on the continuous electrode, which improves the energy density further. If there is something here that drives these things together, it is the fact that transport between electrodes is 1D at the microscopic level. And so by putting things in a non-planar geometry, you are increasing the energy density. It is, as Deborah Rollison says, you are building skyscrapers rather than ranch houses. You're putting more energy per unit area into a skyscraper, taking advantage of the vertical dimension than you are by laying things out in a planar dimension. And so this, as I indicated before, has enormous improvements for micro batteries and for electronic devices. And as we go into IoT, the Internet of Things, it even gets more valuable. So early on, we came up with design rules, certainly design rules for these arrays, in this case, the interdigitated array. And again, it's exactly as I mentioned before. If you want to increase the energy density, you don't make it thicker. That's not going to help your kinetics. You make it longer, and you keep the distance between anode and cathode the same. That's great. Now there's diminishing returns, and that is the fact that as you make the arrays longer, then what can happen is that the ohmic resistance may increase and your fields get a little bit strange, and they're not going to be very effective. So there is a limit on that. But in general, when the aspect ratio is greater than 5, you are better than any 2D system that you can imagine. And in some systems, really, when you get to just L over D equal to 3, it's better. So it does depend a lot on what you're comparing it to. But again, it's exactly as Amy showed before. There's absolutely no question that 3D gives you higher energy and also greater power than 2D systems. Okay, it's been an active field over the past almost 20 years. All those designs that I mentioned, people have made in one fashion or another. They've gone through various fabrication routes, and they've been very successful in making electrodes, making batteries. We'll get to that in a little bit. And so really what we see is that there's been great success in fabricating the materials and the architectures. That part's been great, wide variety of materials. And materials and designs are really, they're intimately tied together. There's that aspect. But if there is something that is, which is in a sense slowed the technology, it has the inability to make batteries. And this just shows you, in a sense, just shows you of the individual electrodes about where things are in this. This is a few years old, and so we just highlighted the UCLA things. I'm sorry about that. But what we could see is that a lot of people early on went towards nanowire systems, and that's great. But really, if you need to store any kind of energy, that's not going to help you. And in fact, it didn't even help the current density very much, of course, either. And so the work that goes on at nanoscale is elegant, it's beautiful, it proves the point, it's just not going to be practical. There are other systems where you can increase the energy density. Again, we're looking at the energy per unit area because, after all, it's the footprint area that's important. And of course, current for the power density is going to be important as well. And you can see there's much fewer systems out here. And really what that represents is the fact of the inability to take a 3D electrode and to then assemble it into a 3D battery. And so as I go through this talk, it's going to be a series of challenges. And each design is going to have its own challenges, but it's a series of challenges. And challenge number one is being able to fabricate the battery. It's really being able not so much to fabricate the electrode. As you can see, this is very nicely done as we do cathode materials. It's carbon, or we could do a variety of other materials. But indeed, to make the full battery, that's the issue. And by the way, this is a paper that Amy and I co-authored a few years ago. Anyway, and it shows the different steps you need to have. And you have to somehow get the electrolyte around it. And somehow after that, you have to get the cathode material around that. And that's what we mean by assembly. This part you can do. This part we'll talk about. This has been really hard. So for a while, we tried to work with ALD and then to use various types of condensation to build up the electrode. And then after that, put a current collector on top of it and the like. And this is really hard to do. And part of the reason is because you're making the arrays in one place, you're depositing it in another place, and you're putting the cathode in another place. Yes, you can do it all in a glove box. It's just really, really hard to do this. So this just gives you an idea about how fabrication can be limiting. So what is better is to think of how can you fabricate with one chip. And so you can do that by MEMS technology or micromachining. And this is an example of what's called carbon MEMS, where you use a photoresist, SU8, and you pyrolyze it so that you make carbon arrays. And by having two different electrode schemes, you can now separate, and you can probably see that better over here, you can now separate one set of electrodes from the other set of electrodes. And so what we did is that on one set of electrodes, we preferentially electrode deposited a conducting polymer, polypyrrole, which could serve as an anode material. And it's not a great anode, but at least you could prove the concept of this. And at the end, here's what you wind up with. It's a beautiful array. It's almost as if it's the way that you drew it. It's thicker because of the polypyrrole that you need in order to match the capacity of the carbon, or at least come close to that and the like. And then you could see the lines of carbon on the lines of the polypyrrole arrays. It works. There's problems. First of all, there's soft shorts, and that's what this one shows over here, because not all the arrays stand up. There was no separator. And so what would happen is that some of these would fall over and you get a soft short. But the other issue, which is actually much more important, is the fact that you have way too much volume devoted to the electrolyte. And so what we learned from this system, because when we determined the capacity of what we should have and what we were getting really, really low capacities. And so because of that, we recognized the fact that, oh my goodness, the electrolyte is taking up way too much of the volume. We've got to do something else. And so the something else was going to a continuous electrode design. So in this case, you start with an array, you then deposit a film electrode. It's got to be conformal to go around the array, of course, and then you fill in the region in between. Sounds like that should work out pretty well. The numbers work out great. If we're to look at the aerial capacity, and again, I reiterate that as being very important for any kind of microelectronics devices because it's the footprint area. Thin film batteries are at most about a 0.5 milliamp hours per square centimeter. And here you can see that with various aspect ratios that aren't even that high, and this is just the diameter of the rods, you can see that you really swamp that. And in fact, for that magic number of a joule per square millimeter, that corresponds to about 10 milliamps per square centimeter. So just up through here. So you can see you have no problem to reach that whatsoever. And this is the chart that tells you also more about that. So there's no question about it. Come up with a design that minimizes the electrolyte, and you should be doing a great job. And the one thing that we did to try to do that, well, we shifted gears and we went to another system where we now literally integrated the electrode with the electrolyte. And in some respects, that's what you saw in Amy's work as well, of this integration of electrode and electrolyte. It's very important. In our case, the electrode was silicon. We're not going to fully lithiate the silicon because we don't need that much capacity. We're just going to partially, like 5 or 10% is plenty for the battery. So you don't have to worry about the silicon fragmenting. You make silicon arrays by standard DRIE processing. Then from there, you're going to use as an electrolyte the SU8. The SU8 is a great photoresist, and it gives you a little bit of conductivity, and especially if you're able to integrate a little bit of the electrolyte into it. And so we're able to do that. Again, you go through standard processing methods, and you're able to get these beautiful arrays of silicon covered with about 10 microns of SU8, and you're ready to go. And from here, we work. So here's the coated array. We filled it with the cathode slurry, which in this case was lithium iron phosphate, put on a current collector and measure it. And indeed, this works. Now the charge and discharge characteristics they're not the most beautiful, but you can see that you do get a couple of milliamp hours per square centimeter, not the design level, which is over 10, but that's okay. At least it's proof of concept of what you can do. And of course, you can run it for a few cycles. And what we found is that, yes, you can get pretty good cyclability out of these systems, but it's only if you cut back on the capacity. And again, you don't really want to cut back on the capacity. So you have to really compromise in that regard. The other part that happens with this is that as you cycle this, and again, you can get cycles out of this, but the Coulombic efficiency drops as well. And so that's another problem. What's the source of the problem? The problem is the electrolyte. It's much too resistant. SU8 the conductivity of SU8 is something on the order of LiPon, maybe just a little bit higher. But when you put it together in a device that's 10 microns thick, then what happens is that you are now, you have much too high of a resistance that you could see it's going to be, it's on the order of thousands. You can't afford to have cell resistance on that high of a level. So what does this tell us? Challenge number 3, low conductivity solid electrolytes. On the left here is a chart of the some of the electrolytes that have been used. And you can see there are some that are 10 to the minus 3, but they're not all that great. For the most part, these are they're much too resistant for the most part. So what we've been doing and have been working on is what are known as ionogels. Ionogels are materials where you combine the sol gel process with an ionic liquid. So instead of using a common solvent like ethanol that evaporates, you use an ionic liquid. It doesn't evaporate, but it does transport lithium ions extremely well. It has a wide electrochemical window, and it has very good conductivity. And as you can see here, the conductivity of the ionic liquid electrolyte, this one or even this one, is orders and orders of magnitude higher than LiPon. So this said, we now had a very good conductive system. The second part of this is to change the design, again, with the eye towards assembly. And that is to simplify the assembly. And this is where we go to 2.5D batteries. With 2.5D batteries, what we're doing is the counter electrode is now going to be a plate. So we're going to make arrays the same way, only now we're going to fill the region in between the posts with our electrolyte. And as long as it's conductive, then you have no problem with it. And then we put on the top electrode, which is a 2D electrode. And that's what we mean by a 2.5D array. It takes advantage of the high energy density or the high aerial capacity, I should say, of the electrode. That part is great. And it takes advantage of the high conductivity of the electrolyte. From the purist standpoint and the fact that we are 3D battery people, it's like, okay, we're compromising our geometries, but we're getting something that works really well. So let me just mention that modeling has played an enormously important part of this development of this field. And this is just modeling that was done by Chris McKelvey when he was a postdoc with Henry White. And he modeled the 2.5D battery system that's using COMSOL. And what he really found and told us that really the magic number was to come up with an electrolyte that was 10 to the minus 3, 1 Siemens per centimeter. Because at that point, then the conductivity would be able to penetrate the entire array electrode. If you lose an order of magnitude, you lose the ability to have access to the entire electrode rod. So this is why the 2.5D battery goes about. And these are our results. This is now for lithium iron phosphate rods, and an ionogel electrode, a lithium top electrode. And you can see we have a characteristic curve that we normally get for lithium iron phosphate. What's nice about this is that the theoretical value of the aerial capacity is indeed 1.5 instead of the 1.4. So at 50 microamps per square centimeter, we just about get theoretical. But what I'm most pleased at is being able to operate at a milliamp per square centimeter, and you are only down by about 30%. So now, of course, we know very well how to design the material so that we can increase the aerial capacity accordingly. But this is the real benefit of the 2.5D battery. The fabrication is a lot easier, as you can see, and also the performance is very good. This just shows you the capacity of the system over the cyclability of the system. And, we've gone a couple hundred cycles and it holds on to its capacity quite well. And then finally, the other part of this has to do with the impedance, still a little high because of the nature of the electrode. However, we have no change in the electrode impedance over time, or the cell impedance over time. And that part is really good. So I'm just about winding up with the talk. Let me just give you a quick comparison of where we are with non-planar batteries. This is a Rigoni plot, but again, it's per square centimeter because for micro batteries, it's the area that's important. The volume is really not that important in that regard. You can see where micro supercapacitors are. They give you high power, no question about that. You can see where the various multidimensional batteries are and how do thin film batteries compare with that. And again, this has been pretty gracious to give them a milliwatt hour per square centimeter, but okay, we'll give them the benefit of the doubt. And you can see that really the multidimensional batteries are up around 10 milliwatt hours per square centimeter. So the field is continuing to advance. We're not there with regard to commercial coin cell batteries, but clearly we are getting close. So with that, let me summarize my talk. And just to mention then that non-planar architectures, without question, are the way to go for anything that's going to be integrated with IoT devices or any kind of electronic type devices. It gives you, in a small footprint where you have limited real estate, it gives you the ability to have high energy and power density. Can you scale this up? Undoubtedly, you can scale this up. And I think actually Amy's already shown that you can scale this up in the sense that 3D batteries are really scalable. What's the challenges? And this is what I've gone through. Certainly the ability to fabricate structures that have exactly everything in place where you want it. That's been a problem. You have to be very careful with that. You need to minimize the electrolyte in order to achieve high density. You don't want a lot of volume that's going to be devoted to electrolyte. And again, you can see that again in the things that Amy talked about. And then we always need better solid electrolytes. So with that, let me thank you, and I'll be happy to take on any questions.
Thank you, Bruce. I'm going to ask again, somewhat quick question for now, and we'll go back to it later. You showed in your 2.5D battery, your ionogels are incredibly good at transporting the ions to give you good rate capability. In the 3D cases you showed a little earlier, despite from maybe having not as good of a solid or gel electrolyte, you also, your pitches and sizes of those pillars were in the tens and hundreds of micrometers for some of these, which was optimized for energy density per area. I understand that. Can you give us an idea how they worked in terms of power just purely by that electrode pitch and thickness?
So their power was limited because of it is not the cathode, it's not the arrays. It was the electrolyte. Right. That was the limiting factor. And so that was all. And so this is why I say whatever number 2 was the fact, or number 3, we need better electrolytes because it really affects the power.
Okay. All right. So we'll keep the other questions for later, and we'll move on to our third speaker of today, which will get us into maybe somewhat smaller length scales than what we've seen in the first 2 talks. So our third speaker today is Professor Sarah Toy, who received her PhD in molecular catalysis for CO2 reduction at UC Berkeley, and followed it up with a postdoc in metal carbon composites for solid acid fuel cells at Caltech in the material science department. Now, she began her independent career as an assistant professor in the Department of Chemistry at Johns Hopkins University in 2015, where she focuses with her group on research and development of porous materials and catalytic systems for energy conversion and storage. And we'll hear some of that here today, again, really looking at molecular architectures really for these materials. Dr. Toy has been recognized with an NSF Career Award, was in DOE Early Career Award, and I'm very much looking forward to her talk, understanding a little bit of this molecular structure, performance influence on the batteries. Please, Sarah, take it away.
Thank you, York. And thank you, Emily and York, for organizing this wonderful workshop. I really enjoyed all the different workshops we've seen so far. So I'm happy to be the last speaker, but we are going to switch gears slightly from new architecture batteries to a little bit more about materials development. My group has worked on tailoring porous materials for use in lithium sulfur batteries, but really, my group has really thought about energy conversion and storage in various length scales of inorganic chemistry and materials chemistry, going from molecules for homogeneous catalysis all the way down to extended solids, and how do we engineer interfaces that allow us to have better conversion processes. Today, I'm going to talk about our work in metal organic frameworks and hybrid materials and how we are designing new functionality to our electrode materials that allow us to have higher battery performances. So I want to first introduce what are metal organic frameworks. Metal organic frameworks, or MOFs, are known as materials are composed of both metal ions or metal clusters with organic linkers that self-assemble to these really beautiful 2-dimensional and 3-dimensional materials that are based primarily by the coordinated environments of those metal ions. These very unique kind of structures have high stability, very high crystallinity, and really are known for their high porosity and synthetic versatility that has led to a whole host of different applications, most notably in gas absorption and separation. But today, I hope to show you that we could also use these metal organic frameworks for electrochemical devices. Really, this type of material is kind of a playground for chemists, right? You think about how just using different metal ions with the same organic linker can lead to a variety of different structures. Here I'm showing you that the zinc ion gives you this very cubic structure, whereas if you use zirconium ions, you get these very neat polyhedrons that are formed using the same organic linkers. Add some functionality to that organic linker, you now get these pseudo two-dimensional materials, make the tritopic versus, and adding other functionalities gives you even more structural variability. And of course, metal organic framers are really known for their isoreticular properties. By extending those organic linkers and keeping kind of the binding groups, you could get a whole variety of materials that have varying pore sizes that enable things like gas separation and absorption. But of course, today's talk is on batteries. And so I want to note that metal organic framers have really interesting properties that allow us to model battery chemistry, including the ability for us to change out these different nodes and linkers and tune the physical and chemical properties of them, adding functional groups that allow us to move charge, but as well as utilizing the pi surface area and porosity for enhancing host gas chemistry. So today I'll kind of talk about lithium sulfur batteries. In order for us to think about being able to completely electrify our society using either through transportation or having access to portable devices, we really have three properties that we need to enhance, right? High energy density, high capacity retention, and of course the ability to charge and discharge quickly. Lithium-ion batteries, that you just heard, have really revolutionized our ability to have these portable devices in electric vehicles. But of course, they're primarily limited, at least in today's current technologies, by low energy density as well as high costs. There are a number of other battery chemistries that we could talk about, but the use of lithium has deemed them as necessarily unsafe, at least at this particular time. So when I started in this field, I really thought about what is the next battery target? And we became really interested in lithium sulfur batteries. Now, in this case, we're still using a half cell where we are using lithium as an anode. But on the other side, we're going to use sulfur to replace things like lithium cobalt oxides. Sulfur is really nice in that one molecule of sulfurate could be reduced by 16 electrons all the way down to a terminal product of lithium sulfide. And that kind of storage ability means that we have really high energy densities as well as capacities. And of course, sulfur is much, much cheaper. There are actually a lot of abundance of sulfur in places like Canada, where sulfur is a majority byproduct of petroleum refining. But of course, there are some major issues, electrochemical issues that we have to solve. One being that sulfur is a poor conductor of electrons. And so getting that first set of electrons into sulfur has a really high activation energy. Sulfur also undergoes volume expansion and contraction that leads to pulverization and mechanical instability. And the one problem that we're going to focus on today is the generation of these lithium polysulfides. As it turns out, lithium polysulfides are quite soluble in most conventional liquid electrolytes. And when that happens, the lithium polysulfides can leach from the sulfur electrode. And then when we go back to charge our battery, we could end up reducing the lithium polysulfide into lithium sulfide on the wrong electrode. This can then cycle back and forth in what is called the polysulfide shuttle. Current materials that are used in lithium sulfur batteries have primarily been carbon-based, and that's really due to the really excellent physisorption properties of carbon. But you'll see here that despite the very high initial capacity that we get in the beginning, at about 40 cycles about charging and discharging your phone, you see that our capacities are much, much lower, about 45% of its initial starting specific capacity. So when we started, we thought, well, maybe we could use some of these really nice, well-controlled molecular materials like metal organic frameworks to understand this process. In particular, metal organic framers have binding sites that allow for the encapsulation of polysulfides within its pores. The organic nature of metal organic framers allow for flexibility to accommodate pore volume changes. And of course, by adding functional groups, we may be able to encourage charge mobility. So we took a lot of inspiration from the solid state chemistry world. In particular, we were really keen on these lithium thiophosphates, Li3PS4 or LPS. These materials are already used as excellent solid state electrolytes, in particular because they have really nice ion conductivity at room temperatures. But as a chemist, what I was really intrigued by was the fact that these thiophosphates can bind to sulfur and form these sulfur-sulfur bonds. So kind of naively, you could maybe imagine a scheme where these thiophosphates could charge and discharge simply by forming and breaking sulfur-sulfur bonds that we have on these thiophosphates. There is a caveat to this chemistry. These thiophosphates are very sensitive to air and moisture, undergo hydrolysis to form things like H2S. And so we need to think about a way to protect these thiophosphates in our system. Lucky for us, metal organic framers are excellent materials for protecting things from reactivity. And so we took a pretty canonical metal organic framer called UIO66, which is composed of these hexanuclear zirconium clusters that bind to this benzene dicarboxylate linker that I've already shown before. In addition to that, we punched some holes into this beautiful framework by removing some of these organic linkers to what is called the linker defected UIO66. If I kind of zoom into a ChemDraw picture of what a zirconium cluster looks like, you sort of see that the zirconium cluster is bridged by these hydroxides. And by punching out some of those organic linkers, we get terminal sites where there's a hydroxide and a water molecule bound to the zirconium. We could then imagine that if we could replace that terminal linker with our thiophosphate, we now have a way to kind of protect the thiophosphate inside this pore and then do our charging and discharging cycle within our metal organic framework. That was the hypothesis. We wanted to see if we could actually incorporate LPS into our materials without degrading it. And we indeed show by XRD, X-ray diffraction pattern, that there's structural integrity of the metal organic framework is maintained largely after introducing LPS. We can also show that the LPS molecule within the MOF is indeed stabilized. Here you see if you take the neat material, Li3PS4, hydrolysis occurs relatively rapidly within about 2 hours. Whereas inside the metal organic framework, we really don't see the hydrolysis product of these phosphates forming even up to 12 hours. We could also play around with how many of these organic linkers we remove, which then allows us to incorporate more or less LPS in order to test our theory. We've also done solid state phosphorus NMR to show that indeed we have a material that's completely thiolated, this phosphorus, but over time our rotor does leak a little bit of air, but it does give us confirmation that this fully thiolated phosphorus does indeed start to hydrolyze over long periods of time inside the NMR spectrometer. We also could use Raman spectroscopy to show that we have a very robust signature of 412 wave numbers indicating of this PS4 vibration. And then if we look at the zirconium oxygen bonds in this cluster, we actually see some profile changes, which gives us a clue that this thiophosphate is very likely bound to that zirconium cluster, thereby changing the ZRO bonds within the zirconium cluster. Finally, we could also use X-ray photoelectron spectroscopy to show that these zirconium clusters are indeed affected by the thiophosphate functionalization. That's shown here. Here, we're using a different MOF, the same zirconium cluster, which has kind of one single local environment defined by these two peaks. If we add in the LPS, these two peaks shift significantly, and we can model that shift with these zirconium sulfur bonds that are now introduced into the system by our thiophosphate. If we look at the sulfur XPS, we do see some similar pictures. We indeed get one environment of our thiophosphate material outside of the MOF, whereas we get multiple environments of our sulfur once it's incorporated into the MOF, suggesting that we are indeed changing the identity of the thiophosphate and its local environment. But with all that, we wanted to know if this works. And so we did a very simple, unoptimized electrode material where we take the metal organic framework, combine it with sulfur, with our binder, which is PVDF, and carbon, and we casted it onto a simple electrode, two-dimensional, onto a coin cell for us to do the testing. When we did this, we saw that using the UIO66 model, where we have 3 open zirconium sites to accommodate 3 LPS units, we indeed see very large increases in our specific capacity that indicates that we get better sulfur access and utilization. And even more importantly, kind of from cycle to cycle beyond the first cycle, we see relatively stable capacity retention. If we use our MOF 808, which is the same zirconium type cluster, but utilizing a different organic linker that enables 6 open sites for LPS modification, we again see an increase in that capacity as well as very high capacities of retention. Finally, we need to test whether it is just the zirconium cluster that's doing all the work. And so what we tested are a non-porous zirconia, which only has open surface sites for thiophosphate to bind. And that's very similar to how we know phosphate binding to the zirconium centers. And when we did this, we see that our strategy of using LPS simply doesn't work. You see a very large capacity to fade. And that indicates to us that the molecular nature of our metal-organic framework, its porosity and structural integrity, is essential in order for the thiophosphate to cycle our polysulfides within the system. We can also do some charge rate capabilities of our batteries, and in every case, from charging from 2-hour charges all the way down to 15-minute charges, we see that our functionalized metal-organic framework always outperforms our 2 other controls. And what's unique about this is that if you took a look at the galvanostatic discharge curves, you start to see some really interesting features. On top here, you see that this is our UIO66 that is unfunctionalized, whereas the bottom one is functionalized. And you see that there seems to be emergence of a secondary kind of plateau here that occurs at higher C rates. And we think that that has to do with the fact that thiophosphate binds to polysulfides that maybe shifts the equilibria of polysulfides within the pores of the metal-organic framework. We think this might be critical for battery cycling. We also see that if we discharge our batteries at relatively high charge rates, we still see high performance even after large cycle numbers. So we took this idea and we thought, well, what we need is not only to optimize for gravimetric energy density, we also need to optimize for volumetric capacities. And so we teamed up with Professor Hersom at Northwestern and his student, Juliet Downing, to look at other ways to make a battery composite. So the first thing we did is that we took our metal-organic framework and we decreased its porosity by melt infiltrating sulfur into its pores. So we no longer have this physical mixture. The sulfur is actually embedded. We also use graphene materials so that the graphene's flatness could actually allow for higher charge conductivity to our polyhedron type battery MOF particles. And what we show here is that the physical mixture of MOF plus sulfur plus carbon actually yields a relatively thick electrode. Whereas if we took our MOF infiltrated sulfur with our graphene, we get relatively thin electrodes both for the unfunctionalized and the functionalized MOFs. What the effect of this is that gravimetrically, we see that our thiophosphate MOFs, shown here in blue, performs well. Now, I will note that we are divided by the gram of slurry material, not the gram of active material. And you'll see that our functionalized material does work really well, but it's not significantly higher than our 2 other materials shown here. However, volumetrically, you see that our capacities actually does shine. We actually get much higher volumetric capacities than our other 2 MOF materials. And that really tells us that this new strategy of making new battery composites is important for commercializing this kind of technology. Finally, I want to talk one more thing about these MOFs. We were interested in trying to use our MOFs for low temperature battery cycling. And one of the key issues in lithium sulfur batteries at low temperature is that we start to see these polysulfides that are generating to start clustering around itself, where the sulfur much more prefer to interact with the lithium than with the solvents that it's in. This clustering kind of leads to poor sulfur accessibility and then eventually some premature deposition that causes our batteries to fade at low temperatures. So we thought, well, if we have these thiophosphate functionalized MOFs, can we use it to disrupt the clustering formation that happens at low temperatures, thereby minimizing this deposition process? And indeed, using the same LPS material that I've shown earlier, we see that in both cases, our functionalized MOF 808 and our UIO 66 material does indeed outperform at low temperatures than the unfunctionalized materials. In fact, at all temperatures that we've shown here. This is interesting because it kind of goes back to what we saw with the charge rate capability tests. What we see here is that using CVs, cyclical voltammetries, we observe that the unfunctionalized metal-organic frameworks have a pretty typical 2 reductive features for sulfur and 1 oxidative feature for sulfur oxidation at low temperatures and at room temperature. But if you have the functionalized material, you start to see a kind of another phase or another reductive potential here that maybe indicate that we have some sort of phase differentiation that's occurring because of our thiophosphate in our material. And so this might again indicate that we are seeing some sort of clustering effect or disruption effect that may be enabling us to have higher specific capacities in our materials. Another way to look at this is that we took a solution lithium NMR spectroscopy. We wanted to see how does the thiophosphate in general disrupt polysulfide clustering. So on top here, you see this is a solution of polysulfides in equilibrium. And you'll see here that as we drop the temperature, you see that the single peak of lithium here start to shift to the right, but also start to diverge. And you can see multiple peaks here at lower temperatures. That to us indicates that there's some clustering that's occurring that leads to these different identities of lithium ions. But if you take P2S5, which is our proxy for our thiophosphate species, and you add it to that polysulfide solution, you'll see that we still see one lithium kind of environment. And that peak does shift right as we lower the temperature, but it always stays as a single environment. And so this is our clue that we think the thiophosphate must interact with the polysulfides in ways that the solution doesn't at low temperatures. Some other ideas, we are not limited to just thiophosphates. We could use organic linkers as well. And so we've done some work using maleiamides as a way to capture some of these polysulfides, showing that these materials do indeed improve in its performance. And we've also done things where we incorporate redox active ligands into our meta-organic frameworks to allow for additional ways for lithium and electrons to be transported within the porous framework. And that's shown here, where we can see really beautiful CVs of these anthraquinone species within our meta-organic framework when we add it to our materials. And we do see some very nice battery enhancements over our controls. And so with that, I hope I've shown you some chemistry about how we've been able to use metal-organic frameworks as a platform for understanding these new materials for lithium sulfur batteries. We've talked about thiophosphates, but we're not limited to using metal-organic frameworks to just lithium sulfur batteries. We could think about using them as solid state conductors, modeling things like nasicon and lysicon, as well as lithium ion cathode materials. With that, I'd like to thank my group. This work has been primarily done by Dr. Avery Bauman, Dr. David Burns, Dr. Shu Han, who have all left us for greener pastures, as well as my student Bing-Chen Liu, who's currently in her 5th year. I'd like to also thank my collaborators that have been able to enable a lot of the work that we've shown here today, and as well as our funding sources. I'll just put one more plug here so that we do have an open battery postdoc position in my group through the work of the New Energy Institute at Johns Hopkins. And so I'm happy to talk about that via email to any interested parties. And with that, thank you.
Awesome. Thank you so much, Sarah. I just love the ability of this molecular architecting that the MOFs and also the COF community provides. And I can see really a lot of a future there in many applications. Now, a quick question for you before we go to the panel session that I had, especially in the MOFs community, was the different metals that hold everything together and the organic linkers, and applying those to batteries. There's two first issues that maybe arise quickly to me. One is, what is their redox stability? And the other one is, what is their conductivity, electroconductivity, and does it even matter, what, depending on the size, I guess, of their crystals?
Yeah, that's a great question. You'll notice that we were using zirconia, the meta-organic frameworks, and that's primarily due to the stability issue you spoke about, right? It's not redox active, so we don't expect it to decompose. And that is a plus for us, but it also is a concern, right? Because it adds a lot of weight to our battery materials now. So we need to be able to balance this ability to add a cathode additive while stabilizing the cyclability, but then also trying to increase our energy density. So we have thought about the connectivity issue quite a bit. We primarily focus on trying to find ways to make our MOFs more ionically conductive by adding functional groups in it, but adding some of those redox active motifs certainly will also enable us to kind of improve electronic connectivity as well. So these are all concerns that we are very much aware of and hoping to answer soon.
Awesome, thank you. All right, so then we will move over to the more general Q&A session and panel discussion, if I can ask everyone. There we are. So I want to remind the audience, if you have any questions for our speakers today, please put it in the Q&A. I believe the chat doesn't work. And the first question I got from an audience, we're going to start with that. Our broader discussion here is regarding 3D battery architecture. So mostly for Amy and Bruce. And the question being if additive manufacturing is a possible solution to control the spatial distribution, essentially, of the functional components a little bit better. Maybe we'll start with Amy on that.
Sure. I think Bruce probably knows a lot more about this than I do, but I would say there's a lot of room to be creative thinking about additive manufacturing. When I first started thinking about the battery that I showed you today, we started with a nanowire array because of a lot of Bruce's predictions, and it turned out to be just so difficult because they were mechanically not super stable, and we didn't have a good polymer. And so we were trying to use these nanowires as a test bed to optimize polymers, and it was just really, really clunky. Back then, I think 3D printing was a lot slower, and there wasn't such an ability to 3D print different types of materials. I think so much has progressed to today that, yeah, I think there's probably a lot of room for improvement there. I don't know what you think, Bruce.
Without question, this is a great direction. Part of the reason is that the dimensions are right, to making small batteries, of the type that that we make and other people make and so forth, which already have a market. But the other part, which I know that Amy, you and I both agree on, is that if anything that simplifies the fabrication, simplifies the assembly, increases the yield, and so forth. So whatever type of 3D printing or any type of additive manufacturing can be developed that makes things simpler, it's going to help without question. But the dimensions are right, everything's right, and you're right. A decade ago the materials weren't there, and they're kind of there. They're still not there exactly. But that's another issue.
Yeah, and one thing I can also imagine an issue. I think Bruce mentioned it in his talk very specifically is, of course, we want to keep the electrolyte, at least in most of the 3D architectures, as thin as possible. But at the same time, as Amy has shown, they have to be highly conformal and uniform as well. So ideal would be almost if we couldn't manufacture an electrolyte that's maybe structurally stable and then coat the other, two open spaces with anode and cathode, but that's not typically the way it's done. And the small fraction that the electrolyte have to take up may be tricky also for additive manufacturing. So that's, it's an interesting way to think about it. Now, to drive this a little bit to the extreme, I actually was kind of curious about maybe a vision or an insight from Sarah. When I look at some of these architectures that Amy and Bruce have shown in terms of 3D batteries, and I just simply look at schematics and look at the MOFs and the molecular architectures that you can build, right? Where can we see an intersection between the two? Not just having, for example, MOFs or such large cage structures be the active material of one of the components, but can we actually imagine interpenetrating MOFs that could eventually form a 3D battery? Is that science fiction, or is there any kind of reasonability behind that?
Yeah, I would like to think so. I guess I hope maybe Amy and Bruce could comment. But I think there's a lot of room here for integration, right? I mean, the porosity of inorganic frameworks is an issue, but it's also extremely porous for you to put things in, right? So you can start thinking about ways to integrate things like solid-state electrolytes, where you start to integrate polymeric materials or ceramics that allow for you to utilize the stability of this framework, but also be able to do charge transport. And so I think there's a lot of room for us to kind of think about how does molecular properties directly translate to a macroscopic property that we might want to have inside these devices. So I think there's still a lot of room for us to play here.
So maybe, and to translate it for Amy and Bruce, I know Bruce has gone essentially somewhat larger in his length scales for his 3D batteries than originally, I guess, was proposed and partially at least realized also by Deborah Rollison. Where do you see the smaller length scales? How far can we push it down? And is it even reasonable to go much smaller than, let's say, 1 micron, 10 micron in kind of these pitches?
Well, let me just say this. There are special applications that the Defense Department's interested in to make batteries sort of less than a millimeter in size, okay? Because literally at that stage, they're no longer visible to the naked eye. So you could imagine, different things like that. That's what I've been told. We've never worked on it because I thought that would be really, really hard to do. That's why. Regardless of the energy and power you could get out of it, I just thought, wow, how am I going to do this? So
I think this is a case for 3D batteries where, other industries have learned how to do several of the aspects of how we have to put these together really, really well. And we could do well to learn from that. So for example, I think about how thin the layers are now on integrated circuits in the semiconductor industry, and, the incredible, just thinking of the size of wafers today and how perfectly materials are deposited with such control. If we could incorporate a lot of that technology, I think like Bruce said, you can make batteries super tiny, super big. I mean, you could use these architectures for a lot of different use cases, I think.
Yeah, let me add, and I think that Amy knows this very well as well, and that is Gary Rubloff at University of Maryland. He works on ALD, and he's published ALD batteries. No, they don't have a tremendous amount of power and energy, but that, of course, is elegant, really elegant, because you do get molecular control. That's very exciting work, I think, in terms of the future as well.
I agree, and I think the knowledge from the electronics industry, which I very much agree, can flow into this in terms of structuring. Also, they're going now to 3D, right? Their classical 2D layers is we're way beyond that. And the argument that used to be as well, that's all physical changes, right? We deal with conductivity and electrons, and batteries we deal with mass transport and chemical reactions. But I think the Rublev group has shown very beautifully that it is possible at those scales if you can manufacture it. Which kind of brings me maybe to the larger picture, and we'll get started with Amy on that question, which is due to her industrial experience here as well, which is kind of the question about how quickly does industry take up these somewhat novel ideas. You guys mentioned it conceptualized in 2004, well before I did my PhD. And when I read about that, I was fascinated and thought, why don't we do that? And I'm very happy to see that Amy is working with industrial partners or taking it up, but it's been taking a while. Like where are these bottlenecks to work with industry to take up these highly, like very much potential solutions to an energy problem?
Oh my gosh, that is like such a deep question. That's probably better discussed over a beer. I think, the problem fundamentally is that industry is not very patient. And so the challenges I had at the very beginning is I was just trying to find this really rich project to work on with lots of graduate students and postdocs over time. I was not intending to commercialize this technology. So I could look at like Bruce's papers, and I looked at all the graphics, and I just thought about, I was just thinking about fun, all the chemistry you could really develop to try to make these architectures. And then we thought about it in terms of someday, if it worked, somebody scaling it. And that's why we tried to pick tools that were very cheap and fast and all that. But the problem then is it doesn't look like a traditional battery manufacturing process. And so early on, when we were trying to raise venture capital money, we kept getting told, well, this won't be a fast exit because no battery company will try to. The assumption was that the goal would be to be acquired by LG or Samsung or a large battery manufacturer. And the problem was they'll never want to change the process because that takes time and optimization. And I think what potentially has changed now is we're getting to diminishing returns in terms of how much improvement can be made on current lithium-ion batteries. They are made in massive volume, but even that volume is not enough to meet all the demands. And so I think people now are more open to thinking about, okay, maybe your process can't drop into an existing battery manufacturing facility, but maybe it could be part of the next generation of battery manufacturing facilities. And so I hope that people are changing a bit and being a little bit more open-minded about process. I'll say all of our strategic partners, we were championed internally by groups that were designed to look for exciting new technology. There were not groups that were looking for already established technology that was being made at scale. So there was an assumption that it would take some time. I think the trade-off is just takes a really long time to get a really good battery first and then to scale it. And so the battery industry doesn't have a very good reputation, I would say, for being honest about the time and investment required.
And maybe along the scale of what is essentially plug and play with industry, Sarah, your materials, the way at least they're grown and they're solid, can probably be very easily incorporated into existing material structures. But that in the end only makes sense if the performance works out and the costs are low. Can you give us an idea more on if you have any information about where kind of the techno-economic direction for MOFs and costs and similar things are? Is there a potential to save money, essentially? You're on mute.
That's a great question. Yeah, I mean, we know that metal organic frameworks have been around for a long time. And there is been some usage, growing usages for in other fields. I think there's an economy of scales that's going to happen with MOS. I can't say exactly where it's going to be, let's say in 10 years, but I think in terms of using MOS for other things besides gas separation, is going to allow us to drive the price down. And the hope is that because we are kind of a drop and play, we mix into our slurries, we might be able to be incorporated into a larger system. But there is currently no lithium sulfur battery company out there that is manufacturing these at scale. So I think the battery technology itself is going to be a challenge for us.
Awesome. Now, one thing that while we're talking already about kind of essentially the battery scale and how the materials properties influence that, one thing that gets often overlooked and was a huge issue in the photovoltaics community around things like perovskite is actually how is that final assembling step of a cell? How do we seal these batteries up, right? We look at the anode structure, the cathode structure, the electrolyte, especially in the 3D batteries, and we think about maybe how to incorporate current collectors. But in the end, for many battery systems, we have to seal them. Amy and Bruce, is that something, well, Amy, you have to have done that. Is that something that was very tricky, or is an issue in this technology?
Okay, Bruce, I will start, but you should answer because your technology is very different. So in our case, it was not a problem because we just package them as pouch cells, which are all that equipment is already known. And I did tell you for a good low temperature performance, we do gel our polymer, and actually the cathode slurry ends up getting gelled as well. And that whole process is already known. So for us, pouch cell sealing is not a problem and it's not new. The problem is we can't package under pressure the way like a lithium metal battery would be. Now, Bruce, for yours, what I think of is, again, thinking about the semiconductor industry, packaging is just really well known for semiconductor devices like that. So I think that's not so much of a problem.
No, it's not as much of a problem. And also there's one word that we always are using in the lab, and that is parylene. You take things over to the parylene coater, it's conformal, and that stuff is incredibly stable. And if you want it to be even more stable, you coat it with parylene, you put a metal layer over that, and then you put parylene over that. It's incredibly good. It's incredibly good. It's got to be integrated with, being able to handle lithium, but that's not an issue. So the packaging part of small batteries is not is really not that much of an issue. What I'm finding though, and this is kind of interesting, is that the people that are the users, the people that want this, they're used to looking at coin cells, and so they're perfectly happy with getting a coin cell. Now being able to package arrays inside a coin cell is not my optimum design, but obviously we can do it. So that, and other people have been doing that as well. So there's that aspect as well, that the packaging parts of things is really critical, but it's not a showstopper, that's for sure. And I think Amy's saying that too.
Yeah, I will say the one spot we have gotten stuck on, because of the electroplating, we can coat basically any shape. And so we have made batteries that's like were ring shaped and wristband shaped. And when Intel had a wearables division, we did have a partnership with Intel. And the problem is we can make a battery in that shape, but nobody knows how to package an oddly shaped battery. So for those examples, I would say it's probably harder, but I agree with everything Bruce just said.
Yeah, just to let you know about current research, we're working with a group. They're funded by an industry. We're funded by an industry group again for wearables, but from day one, it's integrated, and that's the way to do it. So it's a wearable device, but the battery's already integrated in it, and we're already, the electrodes are already in it.
Yeah,
and that's just a great way to do it.
So the next step, apart from integrating and interdigitating the batteries, is to actually build the battery with the design of its application in mind, and as part of that.
Yeah.
Now, maybe just a couple finishing thoughts from each of you, which kind of combines a couple of what things, though over different length scales that you're looking at, is can we also imagine in the future to maybe have something like a self-assembling battery, where instead of starting off with our anode, coating it with an electrolyte, finishing off with a cathode, where we throw everything together with programmed material through, either organic, inorganic interactions or things like DNA, et cetera. Do you believe this has any kind of future? And maybe we'll start with the smallest scale here with Sarah, who knows a bit about the molecular assembly, and then work us to the larger scale with Bruce.
Oh, that's I'm in the hot spot. So yeah, I I don't know how I have a good answer for it. I like to imagine that this can be a possibility. We work on self-assembled molecular materials, and so you can maybe imagine that we can start to assemble, MOF type batteries where you have a MOF anode, a MOF electrolyte, and a MOF cathode that maybe could self-assemble in some way that allows us to use it. But at the moment, I don't have great ideas, and if I do, I'll let you know. Maybe in a couple of years. But yeah, I think it's an excellent point about, where is the future lie for our batteries?
That's a hard question, although I do think, if I remember correctly, that was Yetming Chang's original idea for A123, was a battery where you just mix all the components, they will self-segregate and form a really high surface area structure. I think even just thinking about this webinar and each session, what we are seeing now is not just better tools for making materials and assembling them, but just incredible innovations in computation. And so I think, I always rely on theorists to tell me what a good solution is, and then I try to make it. But I think thinking about the work of like Partha Mukherjee and people like that, being able to understand and design from the beginning, mechanical properties, corrosion properties, and then assembling materials to do that. I think that is possible on the horizon.
We've already done, I think that the community's already done self-assembly in a sense, beyond Yetming Chang's. Because when you do these alternate layers, like Langmuir-Blodgett films that are charged and go from one to the other, you are designing multi-layer structures. And I know that there's been that people have made little batteries out of these multi-layer structures, and that's self-assembly. I also advocate the idea of giving things sort of an electric field push, like electrophoretic deposition, so that you're just a little bit of something, and you can now direct the assembly very nicely. So in some respects, I think it's coming. It really is, and it's already been demonstrated in some respects.
And certainly 3-4 component assemblies with specific succession of layers in 3D and in layer by layer fashion in the soft matter community is something that's very much there. What's missing is the functionality of the battery components at the moment. Okay, so our time is up here. So I very much send out a big thanks to all our speakers and panelists for today. Sarah, Amy, Bruce, it's been fantastic, very informative and inspiring insight that you have given us. I also want to thank everyone who attended the seminar. And of course, another round of thanks to our sponsors here, the Institute for Sustainable Energy at Boston University, the College of Engineering, as well as the Division of Material Science at Boston University. Matt, if you want to bring up the last slide, I do want to quickly point out that the recordings for today's and prior workshops are available through the ISE website that's noted here. And I also want to invite everyone to our next workshop series on the energy of the future, specifically understanding artificial intelligence potential for sustainability. A couple of those workshops are listed here. Feel free to sign up on the website for those. And with that, again, thank you, everyone, and have a wonderful day.
Bye, everyone. Thank you.
Bye-bye.
everyone.
Thank you.
Thank you.
Hello, is it safe to say we could stop?
You can finish and end the webinar, yes.